Today we are going to talk about periodic trends. The periodic trends, periods, and metallic properties. As you go down a group on the periodic table, the elements get more metallic. So the most metallic metal is going to be francium because it is all the way here on the bottom of group 1. As you go right across the periodic table, you get less metallic. It sort of makes sense because the metals are over here on this side, the nonmetals are over here on this side. So as you go towards the nonmetals, your metallic properties are going to decrease. So because of that, francium is at the bottom, and the furthest element to the left makes it the most metallic metal. It has the most metallic properties of all the metals. Periodic trends, atomic radii. The atomic radii is the distance from the nucleus of an atom to the valence electron outside shell. There are two variables that determine the atomic radius of an atom: the number of protons in the nucleus and the number of electron energy levels in the atom. So those two things determine how big an atom is going to be. Let's take a look at how those two things affect the radii as you go across a period. As you go across a period, the atom gains protons. The atomic number increases. You get more protons as you go from left to right. Across a period, the energy levels stay the same. So if you are in group 2, for example, every element in group 2 has 2 energy levels. So that is constant. The only thing that is changing is the number of protons. This increase in the number of protons causes a greater attraction between the nucleus and the electrons in the atom. The electrons are pulled closer to the nucleus, giving the atom a smaller radius as you go across. So for example, if you have one proton and one electron, there's an attraction between them. However, if you add another proton and another electron, there is a stronger pull between 2 positives and 2 negatives. So because there's a stronger pull, it pulls the protons and electrons closer together, thus decreasing the atomic radius. If you add another proton, so now you have one more proton and one more electron, because there is such a great attraction between 3 positives and 3 negatives, the atomic radius is going to be pulled closer together and thus decrease. So as you go across a period, the atomic radii is going to get smaller because you are adding more protons and electrons, and the electrostatic force, which is the positive-negative force, is going to get stronger. As you go down a group, we know that as you go down a group, what are you increasing? What are you adding each time you go down a group? Energy levels. So boron has 2 energy levels, aluminum has 3, gallium has 4, indium is going to have 5. So what do you think happens to the atomic radii as you go down a group? It is going to increase by the sheer physical fact that there are more energy levels as you go down. So as you go down a group, because the number of energy levels or rings increase, the atomic radius is going to increase as well. Yes, the number of protons and electrons increases as well. So based on the previous explanation, you would say, well, cesium has a lot more protons than electrons, but the fact that it has a whole new physical shell is more powerful than the fact that it has more protons and electrons at that point. So as you go down, the atomic radius increases. As you go right across the periodic table, the atomic radius gets smaller. This table shows that trend. As you go down, the atoms get bigger. As you go right, the atoms get smaller. Atomic radii versus the atomic number. So here on the x-axis, we have the atomic number. On the y-axis, we have the atomic radius. So notice that for period 1, as you go across the period, hydrogen to helium, the atomic radius gets smaller. Then, all of a sudden, when you go from period 1, period 2, helium to lithium, there's a huge jump in the atomic radius. Why is that again? Because lithium is adding a new shell. So instead of having one shell, like hydrogen and helium have, period 2 elements have 2 shells. So that's why you see a dramatic increase in the atomic radius. As you go across period 2, though, notice that the radius is getting smaller because you're adding more protons and electrons. When you go from the end of period 2 to the beginning of period 3, notice that there's, again, a large jump between those two because you're adding a new shell. The atomic radii decreases because more protons are added to the nucleus. This causes the electrons to be pulled closer to the nucleus as you go across the period like that. Periodic trends, electronegativity. So there is something called electronegativity. Electronegativity is the ability of an atom to attract a valence electron to itself. So here you have like a nonmetal, for example. The nonmetal is going to have a tendency to pull electrons towards it. The strength of that nonmetal to pull electrons towards itself is called electronegativity. So it's basically the strength or power of that nonmetal. For ionization energy is related to metals. Ionization energy is the energy required to remove an electron from an atom. So it is similar to electronegativity, but electronegativity is the traction of electron towards it. It measures the strength. Ionization energy is the energy required to remove an electron from something. So it also measures the strength, but they sort of work in opposite ways. One is the attraction of an electron towards it. The other one is the removal of an electron from a metal. Electronegativity trends. The electronegativity trends are, they increase as you go right across the periodic table and as you go up on the periodic table. We'll take a look at that in just a second. Actually, let's go back here. Let's talk about electronegativity back here. So the electronegativity is the ability of an atom to attract a valence electron towards itself. Let's take a look as you go across a period first. So as you go across a period, the radius of the atoms are getting smaller. So we have, let's say, we have boron here, we have carbon here, and we have nitrogen here. So these atoms are getting smaller. The atomic radius is getting smaller. So the reason that they're smaller is because there is a greater attraction between the protons and electrons. So which one of these, boron, carbon, or nitrogen, do you think has a stronger ability to attract an electron towards itself? The correct answer is nitrogen. The smaller the atomic radius, the stronger the atom, the higher the electronegativity will be. So as you go across a period, the electronegativity is going to increase. The atoms get stronger as they get smaller. They're getting smaller because there is a stronger attraction between the protons and electrons. Now let's take a look as you go down a group. So you have like fluorine, for example, and then you have chlorine, and then you have bromine. So what is happening to the atomic radius as you go down a group? It is getting bigger because of the energy levels you are adding. So who do you think has a stronger attraction to an electron that appears to be out here? Fluorine, chlorine, or bromine? The correct answer is going to be fluorine. The nucleus is closer to that electron. Here, there's this wide distance between the positive nucleus and that electron it sees out there. So there's a stronger attraction when you have a smaller atom. So the trend for electronegativity is that as you go down a group, the electronegativity gets smaller. In other words, electronegativity is highest at the top of the periodic table and to the right of the periodic table. Ionization energy, same idea, related to metals. So if you have, let's do across the period first, let's say you have lithium, which has a radius of this, beryllium, which has a smaller radius, and boron, which has an even smaller radius. The energy required to remove an electron. So if there's an electron here, an electron here, and an electron here, who do you think it's going to be harder to remove an electron from? Lithium, beryllium, or boron? The correct answer is boron. There's a very, very strong attraction between the nucleus of this and the electron that is not very far away from it here. So it is going to be harder to remove an electron from boron. So as you go right across the periodic table, the ionization energy increases. As you go down a group, let's do lithium, let's do sodium, and let's do potassium. Okay, the radius is getting bigger due to the number of energy levels. Who is it going to be easier to remove an electron from? An electron here sitting on lithium, an electron here sitting on sodium, or an electron here sitting on potassium? It is going to be easier to remove an electron from potassium because there is a large distance between the nucleus that it's being attracted to and the outside shell. So as you go down a group, the ionization energy decreases. So activity, the highest ionization energies are found at the top of the periodic table and to the right. Here is a graph that shows the energy required to remove an electron. So here we have the atomic number on the x-axis, the ionization energy on the y-axis. Notice for hydrogen and helium, as you go across a period, the radius is getting smaller. There's a stronger attraction between the protons and electrons. The ionization energy increases. Okay, it is harder to remove an electron from helium than it is from lithium. Then there's a dramatic drop between helium and lithium. What's happening between helium and lithium? You're adding an energy level. So due to the sheer physical fact that the valence electron on lithium is a whole energy level further away from the nucleus than helium's, the ionization energy is going to decrease. Okay. And then as you go across period 2, though, it increases again because your radius is getting smaller. It's harder to remove an electron from a smaller radius. There's a stronger attraction between the protons and electrons. The ionization increases. Valence electrons versus atomic number. So this one is sort of easy. The atomic number is here on the x-axis. As you go across a period, the valence electrons increase. And then as you go from helium to lithium, the valence electrons go from 2 or 8 back down to 1. And then there's a 1, 2, 3, 4, 5, 6, 7, 8 trend across the period. Alkali metals versus their atomic radii. So we have alkali metals on the x-axis. We have atomic radii on the y-axis. As you go from lithium, sodium, potassium, rubidium, cesium, so this is down the alkali metals, what happens to the atomic radii? Is it going to increase or decrease? You're adding new energy levels, so it is going to increase. So you should see an increased trend for that type of graph. For the alkali metals versus their ionization energy. So as you go down group 1, lithium, sodium, potassium, rubidium, and cesium, their radius is getting bigger. You're going from small to bigger to bigger to bigger to bigger. What happens to the ionization energy? Is it easier or harder to remove an electron as you go down the alkali metals? It is easier. So the ionization energy is going to decrease. So lithium is the hardest to remove. Cesium, which has a giant radius, is easier to remove an electron, so its ionization energy is the lowest. Chemical reactivity down a group. So let's say we have lithium, sodium, potassium, lithium, sodium, potassium. The radius is going to get bigger. So this valence electron is going to be further from the nucleus. What do you think happens to the reactivity as you go down a group? it is going to increase. So the most reactive alkali metal is going to be at the bottom, which is francium, because that electron has a very, very small attraction, or a smaller attraction to the nucleus where the positive protons are, than lithium's electron that is closer to the center. As you go down the alkali metal family, the radii of the atoms becomes greater and their hold on the valence electrons become weaker. The weak hold on valence electrons means a greater chemical activity. Francium is the most reactive metal. So for reactivity, metal reactivity increases as you go to the left and as you go down. For nonmetals, because nonmetals are not losing electrons, they are pulling electrons towards them, their attraction gets greater as you go towards fluorine. So the most reactive metal is francium. The most reactive nonmetal is fluorine. So they are at the opposite ends of the periodic table. So summing this up, this table is called a periodic table because periodic trends occur as you go down families and across periods. As you go down the periodic table, what happens to the metallic properties? Do they increase or decrease? They increase. Whoops, let me go over here. Atomic radii. Let's go across first. As you go across a period, what happens to the atomic radii? It decreases. Why does it decrease? Because you are adding protons and electrons, and there is a stronger electrostatic pull between the protons and electrons. Valence electrons as you go across a period. What happens to the valence electrons as you go across? They're going to increase. You're adding a proton, you're adding an electron, the valence electrons increase. Metallic properties as you go right across the periodic table. As you go from metals to nonmetals, the metallic properties decrease. The ionization energy, the energy needed to remove an electron. Remember, as you go across, the radius gets smaller, there's a stronger attraction between the protons and electrons. It becomes harder to remove an electron, therefore the ionization energy increases as you go right. Let's go down. Metallic properties. As you go down the periodic table, the metallic properties are going to increase. Francium has the greatest metallic properties of the metals. Energy levels. What happens as you go down a group? They increase. You are adding a new shell. And as you add a new shell, what happens to the atomic radius? It also increases. Section 3.2, trends in groups. We will do, actually, let's go ahead and do now. The alkali metals. So the alkali metals are highly reactive. They make hydrogen gas when they are mixed with water. So X stands for the alkali metal. When you put it in with water, it makes H2 gas and a hydroxide. X, again, stands for lithium, sodium, potassium, any of the alkali metals. Most reactive are located at the bottom of the periodic table. Francium is the most reactive alkali metal, also the most reactive metal on the periodic table. Halogens. Fluorine in the upper right-hand corner is the most reactive nonmetal. Reactivity decreases as you go down. So we'll learn later that nonmetals attract electrons, metals lose electrons. So because of that difference, there's an opposite relationship that you will see. The reactivity decreases as you go down because your radius is getting bigger, and it is harder to attract an electron towards a bigger radius. Only missing one valence electron to be full. Very poisonous. Halogens form diatomic elements. So what that means is the halogens, as opposed to being singular F, for example, they are found as pairs F2, Cl2, Br2. They form very strong acids, HCl, HBr, HI. These are some pictures of them. Iodine is purple in color. Bromine is a orange, reddish brown gas. Chlorine is a yellow gas. Reactions with halogens. Halogens make acids. So H2 plus a halogen will make HCl based on a displacement reaction. The most reactive element is on the top of the periodic table. Chlorine plus KBr yields 2KCl plus Br2, but Br2 plus 2KCl yields 2KBr plus Cl2 does not react. The reason being is that here chlorine is going to try to replace bromine, which is the halogen. It's not going to replace the potassium in that reaction. Chlorine is more reactive than bromine, so it has enough strength to basically kick the bromine out. But if bromine is going to try to kick chlorine out, because bromine is not as reactive as chlorine, it's found below chlorine, it does not have enough energy or strength to kick the chlorine out, so it actually does not react. So take a look at this. Fluorine plus 2Ki yields 2Kf plus I2. So here, your halogen is fluorine. It's going to try to replace the iodine. Is fluorine above iodine in the halogen family? Yes, it is. So it is more reactive than iodine, so yes, that will happen. And you can tell if it's more reactive simply by its physical placement in the column. The higher it is on the group, the more reactive it is. Iodine plus 2KBr. So your halogen is I2. It's going to try to replace Br. Is iodine above or below Br? It is below Br, so it is not as reactive. This reaction will not occur. Br2 plus Kf. Bromine is your halogen. It's going to try to replace the halogen F. Is it reactive enough to replace fluorine? The answer is no. Nothing is more reactive than fluorine, so this reaction will not occur. Chlorine plus Ki. Chlorine is your halogen. It's going to try to replace the I. Is chlorine above I in the halogen group? Yes, it is, so therefore that reaction will occur. Noble gases. Noble gases were not listed on the original periodic table. Why do you think that is? Because they did not react with anything, so it was hard to tell their existence. Their full arrangement, they have a full arrangement of electrons in their outer valence shell. In some rare cases, noble gases can form compounds, such as ZeF6 and ZeO4. Uses of noble gases. Noble gases, helium is used in airships and balloons. Neon is used to color lights. Argon is used to fill light bulbs. Krypton is used to destroy Superman. Section 3.3, trends across a period. Transition metals. So the transition metals, again, is this group of metals here in between the two main towers of the periodic table. Much less reactive than alkali and alkaline earth metals. Therefore, they are used in everyday life because they do not react as fast. Copper is used for piping. Iron is used in horseshoes. Jewelry. Gold. Silver. Platinum. Titanium. Steel is an iron mixture. Iron mixed with other things like nickel and cadmium. Transition compounds vary in color. So whereas the alkaline metals and alkaline earth metals are mostly gray, the transition metals have a wide, vibrant array of colors. They can be copper is blue, iron can be red, cobalt can be blue or green. So they have a lot of different colors there. Usually have varying electron arrangements, so they don't follow the valence electron rule that we learned in the last chapter. So they, the valence electrons have to be given to you in a different way for the transition metals. And that is where we will end.